I'm Cody Jones. I'm a research scientist at Google, and today I'm excited to tell you about some recent experimental work from my team in quantum error correction below the surface code threshold. And if you're interested in reading more, there's some citations for the main papers behind this work. Okay, so why do we like quantum error correction? Well, it starts from this simple premise that in order to do useful applications, we think we're going to need something like an error per gate of about 10 to the minus 10. And that's because useful applications will use something like 10 to the 10 gates, we think. And when we look at the state of physical qubits today, we see that the errors per operation in physical gates for physical qubits is significantly higher than this. So you might contemplate, well, how are we going to bridge this gap and achieve the very reliable performance that we need? Well, the idea that we're putting forward is that you can use quantum error correction. And I think other speakers at this winter school have talked about quantum error correction. But the basic idea is that you make logical qubits out of physical qubits, but doing so adds an overhead. So you need to know whether this is working, if it's actually paying off. So, the idea is that then you would scale up and these logical qubits would would have much lower error per operation, and then you can be working in this regime with practical applications. So how can we turn this into a quantitative statement of logical qubits are working? Well, there's one way of capturing the logical error rate in an expression that we like to use at Google, which depends on these two parameters, lambda and d, which is the code distance. So if you have a lambda that's greater than 1, then you would see that by increasing d, you can suppress errors. And so approximately, you can say that lambda is the threshold error rate over the physical error rate. So lambda goes up when the physical error rate is going down. They have an inverse proportionality. And if lambda is less than 1, then QEC is really not worth doing unless you're just running some tests. But when lambda is greater than 1, you actually see that you're getting improved performance. And that's kind of the informal way of thinking about being below threshold, although there are some subtleties. So that's the goal. We want to show that lambda is greater than 1, and not just a little bit, but we want lambda to be significantly greater than 1. In the longer term, I'll say today that lambda is about 2. But in the longer term, we would like something like a lambda of 10, because then we get really strong suppression every time we increase the size of our qubits, which is increasing this distance parameter. So the error correction scheme that I'm going to talk about today and that we're running experiments with at Google is known as the surface code. You may have heard of it before, but the basic idea is that surface codes live in a square planar arrangement, and they look like this. And we actually have two types of physical qubits. We call them data qubits and measure qubits. They're color-coded right here. At its simplest implementation, a surface code is a d by d square of data qubits. In this case, d equals 5. And then interleaved with it is about the same number of measure qubits. There is about 1 measure qubit per data qubit. And so, as we showed in the previous expression, the idea is that if lambda is significantly greater than 1, then we can be suppressing errors exponentially in this distance parameter, which is the side length of the square. So another way you may have seen this plotted before, this exponential suppression of error, is these sometimes called threshold plots. And what's being shown here is if I have different sizes of codes, so distance 3, 5, 7, and then a few other examples of higher values, and I also sweep the error rate, then I can reach very good performance in two ways. I can reach it by making the error rate lower, that's moving to the left here, and I can also reach it by making the distance larger, which is these different traces here. So for any fixed error rate, the gap between these lines, and note that this is a semi-log plot, so this is a logarithmic axis, is a factor lambda. And this actually, there's no mathematical proof that it has to be this way, but it ends up being a really good approximation in practice. And so we see here again that the logical error rate that's achieved is this quantity inside the parentheses, which is the inverse of lambda, raised to some power, and that parameter is the size of the the code, which is defined by the size of the processor. Okay, so that was kind of the preamble. What are we trying to do here? I'll give you now an outline of what this talk is about. So the first part, before the break, is this recent experiment with surface code demonstrations up to distance 7. And I'll talk about some background on our qubits, on surface codes, the experiments, and then some interesting things we learned from doing those experiments. And then the second part, after the break, I'll go a little bit deeper into some selected topics that are related to these experiments, such as controlling leakage errors, which I'll explain what those are as I go, decoding algorithms and real-time decoding, and then a close cousin to the surface code called color codes that are similar but have distinct properties that make them interesting and fun. Oh, and if I'm going and you do have a question, feel free to raise your hand. I'm happy to be interrupted. Okay, so superconducting qubits at Google. This is actually a plot from a figure from a very long ago paper on Josephson junctions. In fact, from the 70s. Okay, so Josephson junctions are what happened when you take two superconductors and two pieces of superconducting metal and you bring them very close together with an insulating gap. I won't dwell too much on the physics, but the important message here is that this creates a nonlinear inductor. Okay, that's not the same thing as like your textbook inductor from E&M. So this nonlinear inductor is really valuable because it allows us to then make an LC circuit, a resonator, but this is now actually a nonlinear oscillator. It's an anharmonic oscillator, and that's really important because it means that we can create a qubit by being able to selectively address energy levels. If the energy gaps were constant between any two states, as you get in a harmonic oscillator, this wouldn't be possible. So here's a diagram actually from UCSB, but work that was carried forward into Google by some of the same people. This is an example of what's known as a transmon superconducting qubit. And in this case, this is a big X-shaped capacitor. That's the capacitor. And Josephson junctions actually tend to be pretty small in comparison. So there's a little tiny Josephson junction there, but it's very important. And so in this device, we have a single qubit, and we can control it using these control lines coming in from various sides. So I mentioned that these are anharmonic oscillators. Here's a picture showing how you can visualize that. So the phase over here, that's the nonlinear part, you can actually see that there are energy levels. Those are the blue lines, and then within that, the wave functions, the energy levels are not evenly spaced. Okay, that's a really nice property because it means that we can selectively control 0 and 1 levels while not having to interact with these levels. Now these higher levels, say going from 2, 3, 4, 5, and above, we can't completely ignore them because we're going to call them leak states. They are unintended. It is unintentional when the qubit reaches one of those states, and it's actually quite problematic. And I'll talk about ways that we measure and mitigate that. So if you have one of these devices, you can control them by driving in microwave pulses. So in this case, it's a resonant microwave drive, and the 6 gigahertz is that energy gap between the 0 and 1 states. And in a very basic experiment, you can see that you're driving oscillations between 0 and 1, which, as I said, that was the goal, to show that you had this anharmonic oscillator where you could address the 0 and the 1 states controllably. So in addition to that, you want to be able to observe those states. And so this readout resonator, which is weakly coupled to the qubit, allows us to distinguish the 0 and 1 states through a dispersion relationship. And so that means that we basically take a microwave tone, we bounce it off the qubit, and the phase of what comes back tells us if it was a 0 or a 1. And that's shown here, where the output phase is a strong function of whether the qubit was 0 and 1. Okay, so these are the basics of how we define our qubits, and much of this is true for other superconducting qubits in other teams as well, although there are slight variations. You have, at least for trans ones, you have a large capacitor, you have a Josephson junction, and you have microwave control lines, and additionally we also have flux control lines, although I won't spend too much time talking about that. So when we measure the qubit, this is actually the signal that we get back. In fact, it's the signal iterated something like 1,000 times. So every time you bounce a signal off of this qubit, if it's in a 0 state and you had some idealized measurement, you would get a single point right here in the middle of this cloud. But because of various noise effects, including limitations of our amplifiers, these readout points don't land perfectly where you want them to be, but they still form a nice kind of cloud-shaped thing. And if the qubit is in the 1 state, you get, and this, by the way, is deliberately prepared 1 state, you get a cloud like this, but you'll notice there's a little bit of carryover where sometimes preparing in the 1 state, it looks like a 0 and vice versa. There's a little bit of blue over here. So this is actually how we characterize the quality of our readout, and what's left over, where these, say, red dots on the left-hand side, that is readout error. That is when we tried to, we knew what the state of the qubit was by design of this experiment, and then the result we got back from readout was different, and that is a way of quantifying what is the readout error. So quite literally, if you want to know the details, the axes of this plot are the two in-phase and quadrature elements of the reflected microwave tone. And then when we plot them in 2D, we just draw a line, and this line is, we draw a line through the middle. Anything to the left is characterized as 0, to the right is characterized as 1. And how you draw that line is just through calibration. We run this experiment and we find the best line to draw between these two clouds. There's a question in the back. So there's no, it's just I mean, that's a really good point. There will indeed be some preparation error as well. So calibration of qubits is a somewhat complicated process, and it's also iterative. But in this case, the single qubit gates the reset itself, which should put you in 0, is a quite high fidelity operation, significantly better than readout. And the single qubit gates, once they're calibrated, also significantly higher fidelity than readout. So indeed, there will be some preparation error and single qubit gate error present here, but it is a small part of the budget. The readout error does dominate. Another question.
Do you guys use like a support vector machine or like k-means clustering to draw the line?
That is a really good question. I think that right now what we're doing is fairly primitive compared to that, and it seems to work just as well. I mean, I'm maybe not the best expert to speak to optimizing readout. Something that you can kind of see here that is an interesting part of the story is, let me go back a little bit. Okay, so there's a little bit of blue over here, right? So sometimes a 0 looks like a 1. But if you go forward and you kind of look at it, you're like, actually, there's more red over here than there was, more red on the wrong side than blue on the wrong side. And that is because of T1 decay. So superconducting qubits are biased to decaying into their ground state, and so that happens during the readout process and can lead to more often readout being misclassified, a 1 being misclassified as a 0 happens more often than the other direction. And so efforts to improve readout focus on that rather than like optimally drawing this line, which is a little bit involved, so maybe we could talk about it during the break.
So when you do experiments, do you always run 1,000 times, or they just?
Oh, I mean, I picked a number 1,000, well, because it's on the slide, but like, I don't think there's any constant. I think it's at the discretion of the experimentalist.
But what's the typical value?
I think 1,000 is typical. You know, this would go pretty fast.
Can you also go back to show the slides of the transform qubit, the actual dimension of that? Yeah, this one. So this is in micron, but your readout circuit is much bigger. Is that right?
Yeah, so I guess you can see a length scale up here of 200 microns.
So, wow, so it's almost like 100 times larger.
Yeah. Maybe I should be repeating the questions. I don't know if they're being picked up for the video. But the question was about the relative length scales of the qubit and the readout line. I don't actually... It does pick it up? Okay, thank you.
Unless people can't hear.
Yeah.
I think it helps the back.
Okay.
Okay. Well, I have to admit I'm not the best person to talk about device geometry. So, if I may, I will move forward to finishing up on the basics of our controls. Oh, yes, there's another
Just
question.
one more question about the slide before. I mean, so you kept saying that like we mislabeled some ones appeared as zeros and was mislabeled. Why is it not that they just became zeros and they actually are zeros? Like the ones that are all the way really off in the tails, why are we not just saying that those decayed? Are we still labeling them as ones?
Well, so it's a good question, and semantically, they are zero when they're measured. But what we were interested in is what was the state of the qubit before we started the measurement process. Because if we wait long enough, they all become zeros. So that is not actually telling us what we want to know. What we want to know is what is the state of this qubit at the instant that we start measurement, because it presumably holds some information from the quantum circuit that it has gone through. Yes, another question.
It seems the Google and IBM are using different types of superconducting qubits. Are you both using transmons, or can you explain the difference between your technologies and what are the pros and cons?
Well, that is a pretty involved question. I also can't speak with authority on IBM's qubits, but to my understanding, IBM has focused on what are known as single junction or non-tunable transmon qubits. And maybe if I go back, and I'm not saying that's exclusive, I believe they may have also studied tunable. I'm just, going off of my best understanding. But at Google, we make these double junction qubits. So there's actually two Josephson junctions, and this is kind of cartooned here. And if you could really zoom in, you would see it there. The advantage of doing two junctions is that you can control the frequency of the qubit using one of these control lines. Here it's known as flux bias. So by sending magnetic flux through this loop, we can tune the frequency of the qubit. This provides an extra control knob. So that extra control knob is very useful. In fact, the next slide that I'm going to get to talks about how we use it for gates. However, generally speaking, these qubits have shorter coherence times because it's almost a principle of building quantum hardware that the more control knobs you have, the more opportunities you have for the environment to disturb your qubit. So I think that's the high-level summary, and maybe, again, we could have a deep dive in the break. Okay. So it is actually a good question, or a good point to bring up tunability, because it's important to how we do two qubit gates. So you can bring two of these qubits close together. And remember, these are big capacitors. And so right here, you have two metal pads close to each other, so they also have a capacitive interaction to each other. And for qubits, this will actually turn on a swapping type interaction. Now, there are various ways of utilizing that swapping interaction, but what we really like to do is we like to be able to tune the frequencies of our qubits so that we control when they're in resonant or not in resonant with each other. And so there's actually kind of an interesting trick. It's an old trick. It's from a long time ago, in 2003, but if you start to play games with the energy levels of these qubits, you can bring the 1-1 state, so that's a 1 state for each of the qubits, in resonance with the so-called 0-2 state. That is where one of these qubits is in the 0 state and the other one is in its second excited state. If you do a full swap and then swap again, it sounds like you're doing identity, but it turns out you pick up a phase. And so you pick up this -1 phase, and so this is a fairly natural way to do the controlled Z-gate. And for those who are familiar with, say, error correction circuits, this is locally equivalent to the controlled NOT gate. So that is our main way of doing entangling gates. There's a few other options you could pursue in this architecture, but this is the one we do most often. And we turn the gate on and off by moving these energy levels up and down. And that's where that tunability comes into play. So it is now a tunable interaction where we can turn it on and off very fast. Our typical CZ gates are 20 to 30 nanoseconds in duration. Okay? So, another question.
Which qubit is the control qubit in this scheme?
Well, that's a good question. So we call it a controlled Z gate. It turns out that the gate is symmetric. At least for the qubits, it's symmetric, meaning that it applies a -1 phase if both qubits are in the one state. So there's not really a distinction of which one is the control. You could label it either way. The gate is actually not symmetric with respect to leakage. As you can see, these two states, those are leak states, are different. One of them is resonant, one isn't. And I'll talk about that a little bit later because leakage is actually a nuisance for error correction. Oh, yeah. So maybe try to understand your question a little bit better. We can tune these energy levels, and so we could bring 1, 0 and 0, 1 into resonance with each other, and that implements a different entangling gate that's starting to drive swapping interactions in the first excitation subspace. What I mean by that is the two states for which you have a single photon in the system. And this is actually up in a two excitation subspace. But yeah, there are other entangling gates available if you choose to operate in different parameters. Simply put, the CZ gate and its relation to the C0 gate just has a lot of It's very amenable to quantum error correction. There are ways of using other gates. We have some papers on using so-called I-swap gates that are based on this interaction. But a lot of QEC theory is built on C0 gates, and so it's why it's kind of our preferred approach. Yes, another question.
Quick follow-up. So you would change the states that you tune to do different types of gates?
Well, specifically, we're changing the energy levels here. So we can we can change, say, the gaps between these two states, turning on or off resonance. But this tunable interaction is not taking excitations. Like it won't take a 1 to a 0 or vice versa. We do that with microwave gates.
So say you have to do a Caesar and a swap. How would you do it?
There's a couple of different ways. You can decompose this into a sequence of CZ gates if you're saying, I only want to use the CZ gate. The reasons why you might restrict yourself to that is calibrating these gates is tricky. And so having just one gate to calibrate really well may be advantageous over having multiple gates that you have to calibrate simultaneously. That's just a practical concern. But assuming you are okay with that, you can actually get what you asked for, the CZ and a swap, using only the single excitation manifold.
You would do more than 2 rotations for the CZ?
No, you actually would do a different gate down here that is a so-called I-swap gate, which is a single swap operation between these two states. And you also pick up a phase of I, the imaginary unit I, when you do that. And that's why it's called an I-swap gate.
Yeah. Thank you.
Okay, so those are the building blocks for our hardware. And now I'll talk about surface codes, which is good because I survived the hardware section. Okay, so we're interested in running a surface code, and this is just a 3D cartoon. If you imagine one of our devices, this is what it looks like. It's a grid of 105 qubits. And instead of a single physical qubit, you can utilize some real estate here to place a surface code. And in fact, you can place surface codes of different sizes. So let's kind of dive into that. So here are 3 different surface codes. And when we talk about scaling the surface code, what we mean is making this grid bigger and bigger. It provides more error protection when it gets bigger and bigger. However, remember, we also have this concern about the threshold or lambda. This is only worth doing if errors go down when you make the system bigger. That's a key part of the story here. You're showing error correction is working if a bigger code leads to lower logical error rate. So distance 3, distance 5, distance 7, remember that's the side length of this square for the yellow, the data qubits. And so at distance 3, we can say that in a certain error model, we are resilient to any single error happening at a time. And at distance 5, error suppression is improved. We're resilient to 2 errors, or at distance 7 to 3 errors. It should be noted that that's sort of like a baseline. You can have, in some cases, more than 3 errors or more than 5 or 10 errors, but if they're sufficiently spaced out in time, the code is still resilient to that. So there's a certain neighborhood effect. You can tolerate 3 errors within a certain window in time. So what does the surface code cycle look like? This is kind of now an exploded 3D diagram showing from the perspective of these qubits as they go from left to right, they're flowing in time. And so we might have one of our qubits being initialized as a 0 state, and then it goes through a Hadamard gate, and then it's experiencing CZ gates. This is the diagram or the symbol for a CZ gate with its 4 neighbors in a certain sequence, and then a Hadamard in a measurement. So you probably saw in the error correction tutorial that we call this a syndrome measurement circuit. And so this is a single surface code cycle from the perspective of just one qubit. And so from the perspective of its neighbor, there's something very similar where this data qubit will be interacting with, in general, 4 neighbors, 4 blue measure qubits, and also go through some Hadamards, some CZs, and then something added here on the end is dynamical decoupling, which is a way of protecting ourselves from low frequency noise during the readout process. And so it may be a little bit harder to follow, but this is both of those at the same time. And the key part of this diagram, even if it's not the easiest thing to read, is that every qubit is interacting with something almost all the time. So error correction is just continuously running. We never stop to look at what had happened. We're always running error correction when we need to keep the logical qubit alive. And so another way of visualizing this is if we only look at the CZ gates that we're doing, this is a top-down view. And so in the first layer of CZ gates, they're all happening simultaneously. You can see that almost every qubit is participating in a CZ gate, with a few exceptions like guys on the edge of the code. And then the next CZ gate layer, again, it's simultaneous operations almost everywhere. So this is how error correction works in this system, is that you are continuously checking for errors. At the end of the cycle, there's measurement, and that measurement is revealing to you the value of these parity checks. There's a question earlier about what's important with readout, and we actually want to know the state of the qubit right before we start the measurement, because that is the most information we can get about whether a parity check has been violated. Okay. Oh, question, yes.
How is the reset being done on the slow qubit?
Simply put, we bring the qubit into resonance with a lossy resonator, so the photon is pulled out of the system and decays.
Oh, I see.
Yeah. So I guess I'll just go ahead and mention, in terms of proportionality of time, all of these operations here with gates, these unitary gates, they're quite fast. They take a few tens of nanoseconds each. And almost all of the time in the cycle for our hardware is during measurement and reset. Now, of course, these are parameters that are specific to our system, but it is interesting to note that 70% of the time is actually just this measure and reset. And these operations are quite fast in comparison.
If a qubit is entangled with another, when you reset it, would it affect the other qubit?
Well, I'm sorry, do you have a follow-up?
How do you make sure it doesn't affect?
Well, There's two parts to that question. There's the simple part and the not simple part. So the simple part is that we do reset right after a measurement. So we've already measured the state of that qubit, which means that we've removed any entanglement that would have existed up to that point. And then the not simple part of that question is, why is that okay? And the reason why it's okay is the circuit is designed to measure parity checks of the code. So before you do the measurement, the entanglement is essentially the system being in a distribution of error states, and the measurement forces a collapse into specific errors. Now, if you just do that collapse on its own, an error happened, but you don't have any knowledge of what it was. So the readout, the measurement you get back is really important. It is performing this projective collapse, forcing you from superposition of errors into specific error, and giving you bits of information about which specific error. So that's why it's okay that the entanglement is destroyed in the process. Question over here. That's right. We're doing interleaved X and Z parity checks. Maybe I should go back a little bit just to, oops. I probably should have said it to be a little bit clearer, but there are squares that are like light and dark, say light blue and dark blue. And so they are X and Z. And it almost doesn't matter which is which because they're both surface codes. You just have to remember which one you picked. But there's a checkerboard pattern to these X and Z parity checks. Another question.
I'm just curious, so how long does like the measure and reset take compared to, let's say, a CZ?
Well, oops. I don't know the exact numbers off the top of my head, but I'll try to do the best I can. This whole cycle time, all of these operations together is approximately 1 microsecond, 1,000 nanoseconds. These gates are a few tens of nanoseconds each, so I believe that they add up to something between 200 and 300 nanoseconds right here. So measure and reset is something like 700 nanoseconds total, and I think measurement is more than half of that. So I can get you exact numbers because they're in the paper, but that's off the top of my head about the breakdown.
How about you said it has 2 or 3 errors at a time? So are they selected randomly? Which qubits will have errors?
In a sense, yes, which qubits will have errors is selected randomly because many errors that happen occur in superpositions. And so the measuring the stabilizers will project you out of a superposition of errors into specific errors. So yeah, there is some randomness, which is to say that if you somehow could inject unitary errors, like you're controlling the errors themselves, and the circuit, you're just repeating exactly the same unitary circuit, you can still get randomness in the measurements because of that waveform collapse when you measure the stabilizers.
How does the cycle duration depend on the code size?
I'm sorry, what was the first part of the question?
How does the cycle duration depend on the code size?
How does cycle duration depend on the code size? If everything is going well, it doesn't. We can make larger and larger chips, extending them in space. And in principle, we can run the same surface code cycle independent of code size. Now, I don't want to overpromise. Of course, every device has its own properties that you have to adapt to. But generally speaking, the surface code cycle is independent of the distance parameter.
So, how does the dephasing time compare to T1 and how does T1 compare to the idle time?
T1 compared to which?
The idling time.
The idling time. Let me see if I remember. This is another detail from the paper, so I can confirm exact values, but I believe T1 was 60 microseconds or maybe 80 microseconds, something in that range. And the duration of the cycle is 1 microsecond. Yeah, so almost 2 orders of magnitude, but not quite. Yep.
After you measure, an error syndrome, you then project some poly operator to correct it, right after. Is that in the cycle too?
Okay. So I'm going to touch on this in a little bit. What do you do with these readout readout values that you get. The short answer is that you have to collect them over several rounds, and you have to run a processing algorithm on this history of measurements that's known as syndrome decoding. And I'll talk a little bit more about that. Okay, so implementing the surface code. So this again is a top view of our device. There's 105 qubits. If you're curious, each row is 7, and there are 15 rows. And so what we've shown here is kind of a summary view of the error rates in this system. So the way to read this diagram is the x-axis is error probability for some given operation, and the y-axis is cumulative probability. And so these are cumulative distributions. So for example, that means the very best single qubit gate is down here, the very worst is up here, and everything in between is their sorted values. So for example, at the midpoint, that is the median value of an error rate for that particular gate. And I guess for visual aid, the means are also shown as these kind of faded lines. So you can see that our single qubit gates are the best. That kind of came up earlier as part of another question. Error rates are a few times 10 to the minus 4 for median. CZ gates here are about 3 times 10 to the minus 3 is the median value. The measurement errors here you can see are of order 1%. So that's, for example, how much bigger they are than single qubit gates, more than an order of magnitude. The idle error is the amount of error that's experienced when the data qubits are idle during measurement and reset. So that is more or less the duration of measurement and reset divided by T1. It's with some proportionality. And this other cyan or light blue is simply showing what is the probability that we see parity flips. The DET means detector. It's a kind of a jargon term, but it means probability of parity flipping. Okay, so this is placing a surface code on this processor with these performance benchmarks. And so this is the largest surface code you can fit. It's a distance 7 logical qubit. And the property of the surface code is that the logical operators are string-like, and they point in different directions. So in this example, the Z operator, which is green, is a horizontal line from left to right, and the X operator, which is black, is a vertical line. And they span the length of the surface code, and that is how we can make better we can make better performance by increasing the size of the surface code, is we're making these logical operators bigger. Yes, a question?
Sorry, for the DET, what parity are you checking? The DET.
So this is the average over all of the parity checks in the code. So a single point here, say this guy at the bottom, the best value, that's going to be the best of all of the parity checks in this code, of which there are almost 50. So somewhere in there, one of them is the best. It means it shows the fewest, the lowest rate of parity flip events. And then the median value is the median of all of them. Yeah.
But this is just over one QEC cycle.
This is averaged over many QEC cycles. In fact, I suspect it's averaged over many shots, so it could be over thousands or millions of QEC cycles. Yeah.
But this is not technically an error, right? It can be that the parity check is correct, but then there's some poly error happen. That's why it turned.
Yeah, that's right. So a parity flips when there is some error. It could be an error in the readout itself, or it could be an error on a data qubit, or even a combination of those two. But the fact that it's flipping means that errors are happening. And this actually serves as like a rough performance measure of the system. We know from previous experiments that when you're at the threshold, the detectors will be flipping about 20% of the time. That was actually a previous paper, though actually this one right here. And now they're flipping a little bit less than 10% of the time, which actually happens to that was about a factor of 2 improvement, which also happens to correspond to the logical qubit having a lambda of about 2. They actually end up being kind of close to each other.
Yeah, so is there a reason for the idle error to be very similar to measurement error? Is it because the measurement is happening during idle time? Or?
So it's a good question, and no, I don't think that it is guaranteed to be like that. So there's it's kind of half and half in that there are some ways in which they're sensitive to the same noise. They're both sensitive to T1, but not in exactly the same degree. The reason for that is measurement is more sensitive to T1 in the beginning of the readout process, whereas the idle operation is sensitive to T1 over the entire duration. But there are other errors unique to readout or unique to idling. So there's some common source of error and some different source of error. And the fact that they end up being on top of each other is partly a coincidence, that the distinct sources of error ended up being about the same. Okay, so this actually is a visualization of errors and how parity flips happen. So again, if you think of time as moving from left to right, each one of these diagrams is from here to here is a full error correction cycle. So there's a few error correction cycles that are shown here. And if you look a little bit closer, what is shown is the action of individual errors in the circuit. So when we're running error correction, we don't actually know where errors happen. But what we can say is that for a given error, what would the effect be that it caused? So this is related ultimately to decoding, where we try to guess which errors by knowing the effects of knowing the errors that could have caused the effect we observe. So for example, if there's a single data error here, then it will propagate through this circuit, through 2 qubit gates to some measured qubits. And then ultimately we measure that 2 parities flipped. And that's because those 2 stabilizer operators, they actually touch in a single place, which is the data qubit that had an error. So if that data qubit has an error, the 2 neighboring parity checks flip. And that's like a distinctive signature of that error. And there are other variations you can have where you have an error in the middle of the circuit, because that's an important thing to think about. It's not just, you can't assume these gates are perfect. So in the middle of the circuit, you can have an error, and it can actually propagate to a parity check here in this cycle, and then doesn't even show up later on its neighbor until another cycle later. And you have to account for all of these possibilities. But they're all kind of distinctive signatures of errors. And there's this process known as decoding that will look at all of the measurements together collectively and assign what it thinks are the errors that happened. Okay. So now kind of explaining part of the experiment that we did, we have this large processor, large in the sense of being able to hold a distance 7, but we can actually fit multiple instances of smaller codes on the same chip. So for example, with distance 3, we can put distance 3s in many locations. There's a lot of space. And we didn't do every possible one, but we did what we call a covering set, which means that like we used as much of the chip as we could to get representative for D3, distance 3, meaning like, you know, we don't want to pick like the best position. We want to pick all the positions so that we're kind of sampling average distance 3 performance rather than an arbitrary choice. Likewise, with distance 5, we moved into 4 different positions, and then distance 7, we have only one option. So this is actually kind of the main result of the experiment. And there's a lot of data here, so I'll spend a little bit of time breaking this down. So what we have here is 2 plots. On the first plot, this is an integer value for number of error correction cycles that were run. So all the way up to 250 cycles. And then for each value of number of cycles, we ran the experiment some large number of times. I think like 50,000 or 100,000, something like that. And so every time we run the experiment, we get a single bit out for the logical qubit. And the experiment is simply, were we able to keep the qubit in the right state? So if we kept the qubit in the right state, then the logical error probability for that one shot is 0. And then for the shots where it was the wrong value, well, the outcome is 1. That single shot was wrong. So the average over 50,000 shots is what is plotted here by each of these points. We've shown some fit lines to them. These are essentially exponentials. If you think about the coherence of the qubit, the logical qubit, it's an exponential decay. But the way we're plotting it is actually an exponential rise in the error rate, because the error is like the inverse or the complement to fidelity. So if we ran these experiments long enough, they saturate to 50%. That's because the logical qubit will end up being random if you run it for a long enough number of cycles. And so from these fit lines, we can extract an error per cycle. It is, of course, a nonlinear fit, and that's necessary because they will just saturate to 50%. But in the beginning, it's mostly linear, so you can think of that logical error per cycle as the slope right here. So lower slope is better, that's lower error rate. That means that the logical qubit is performing better. And we have a coloring scheme here where for red, that's the distance 3s, and they're decaying to their 50-50 random value fairly quickly, at about 250 cycles. And then the light blue, that's the distance 5, it is performing better than the reds. It has a longer coherence time, or error is building less quickly. Just for general interest, we showed what would be the performance of a bare physical qubit. So the distance 5 codes are on average slightly outperforming the average physical qubit. That's interesting. But we have distance 7 down here. And so distance 7 is continuing to perform even better. Now, I said that there's a fit parameter that is the logical error per cycle. And informally, you can say that's the slope here. It's actually a fit for the whole thing, but in the beginning, it's kind of the slope. And so that is what is now plotted here, the logical error per cycle. So that's extracted from this plot. And here we just have the 3 distances, 3, 5, and 7. And so there are multiple points when we have multiple instances of the code. So all the distance 3s are here, and then their median value, or maybe it's the mean, it might be the mean value, is right there. And then likewise for the distance 5, and then the single point for distance 7. And so one of the particularly interesting parts of this plot is that we can draw a straight line between these 3 points. I said at the beginning of the talk that we have this expression that is 1 over lambda, the inverse of lambda, raised to a power. And that was kind of an aspiration, that that's what we would get. And previously we had an experiment where we had distance 3 and distance 5. Well, on its own, you can always draw a line between 2 points. Okay. But when you have 3 points, and then hopefully in the future more points, you can really test this hypothesis. Is error correction working? Where every time you step up the size of the code, you get this suppression factor that we call lambda every step up. And of course, we've only shown it so far to distance 7, and then as we go forward, we want to show it to even higher distance. But seeing it this way is actually kind of exciting, I think, because at least it's corroboration that the methodology really is holding up. And perhaps just something else that makes us feel better is that this is simulation in this inset, and the simulations are parameterized with experimentally extracted values. Remember I showed the plot of what are the CZ error rates, the single qubit error rates, and so forth. If we plug that into a simulator, we're seeing pretty good correspondence. Now, it's not perfect, and I'll maybe talk a little bit about what are some of the gaps there. But this is actually, it's encouraging that if you look at the sort of the scale here, we're not off by a lot in our simulations. There's some noise that we don't fully understand. I'll address a little bit of that. But the simulations say that we should be seeing this linear performance, and at least so far, our experiments are tracking that, and that's very encouraging.
Is the physical qubit dynamically decoupled here, or just?
Yes, it is. Specifically, if I go back a little bit, the data qubits, So I'll try to remind you what the different color schemes mean. So the blue guys are the measure qubits. They're the ones that are providing parity checks. And then the yellow guys are the data qubits. So we don't measure them directly until the very end. And so if you follow this yellow line, you'll see that the data qubits are undergoing dynamical decoupling at the time that the readout qubits are being measured and reset. So it's
Hold on, specifically on your chart.
Okay.
Line with a physical qubit.
Oh, yes. You're saying with this physical qubit was, I misunderstood. Yes, this is with dynamical decoupling. Dynamical decoupling can only take you so far because T1 is essentially a memoryless process that you can't fix with dynamical decoupling. And so that's what's happening here is you're being limited by T1.
So
yes.
in the end game here, like you talk about 10 to the minus 10 logical error rate, like the scaling is still like exponential decay, and what would be the, kind of the range of this?
Good question. I know I have a slide for that. Maybe it's coming up. Well, I'll go ahead and answer your question. There is a slide, I think, later in the talk about that. If you have this line, and you say that this line is actually an exponential because this is a log-scaled axis, then if you want to get to 10 to the minus 10, well, you can keep following it down. And now my laser pointer is going off the screen, and it's going down the chalkboard. And it goes really far until you get to 10 to the minus 10. And that's because lambda is only 2. And that means that you have to raise 2 to like some really big exponent to get 10 to the 10. And the inverse of that is the error rate. So we need to have a higher lambda. A lambda of 2 is error correction is just kind of working and is arguably not enough to scale the technology. So even though there's technically a solution, an exponent that gives you what you want, the answer is surface codes that are so big and so difficult to make that it seems daunting that you would actually pursue that. And a much better path is to try to make lambda higher. So you need a smaller size code.
So in principle, regardless of the lambda, the figure on the left is the same, right? If you have the same 10 to the minus 10.
So on the left, if lambda was bigger, you would see these curves spacing out, right? So they would all come down, but the ones that are at higher distance would be coming down even faster. Because this one is actually chordically sensitive. Remember, the exponent is d plus 1 over 2, so 7 plus 1 over 2 is 4. So this is actually fourth order sensitive to lambda. This one is third order, and this is second order. And so they would all be coming down if lambda was improving, but they would be spacing out as well because the higher distance ones are dropping faster. Yes.
So if you want to increase lambda, of course you can reduce the error rate, the physical error rate. Is the threshold a constant or something you can play with?
So the threshold is often presented as a number, and the reality is much messier than that. The reality is that you have multiple operations in your circuit, your CZs, your readouts, et cetera. They have independent error rates. So much of the traditional QEC literature that computed threshold says, imagine they all scale proportionately. But in the real world, they don't, because you might make an improvement to readout, say, to make that more reliable, but that doesn't affect your T1 time, right? That's a separate source of error. And so what that means is that the way to think about it is that there is a weighted source of these physical errors. So you sum them together with weights of proportionality and then compare that to some threshold value that is mostly constant. And we have some information on that in the supplements of our papers, which I could show you later if you want to. But the story is a little bit more nuanced when you have a multi-parameter error model. Yeah, go ahead.
It seems to be that for quantum error correction, you have to have a balance between increasing lambda or d, and increasing lambda is reducing the physical error rates and increasing these more physical qubits per logical qubits. Can you compare the two a little? Because I thought that we've reached an edge of increasing lambda, but you were saying that we should try perhaps how do you do that? How does that compare with increasing D?
So one way to think about it is that lambda is an intensive property and D is an extensive property. And what I mean by that is lambda measures the quality of components. So it is actually addressing the previous question that there is a way of assigning weights to the different sources of error. For example, the 2-qubit error rates matter more. They are weighted higher than almost anything else. They make up like half of the error budget. When you do that, you're really just, you may be assuming that there's kind of homogeneity. It's a decent assumption that most of your CZ gates are about the same. If you remember the distributions from here, they're not, if they were all identical, these would be vertical lines. They're not really vertical lines, they're distributions. But, you know, the 1-qubit gates are over here and they're in a certain band, and the 2-qubit gates are over here in a certain band of values, et cetera. Lambda is kind of, it's measuring the average performance of your components appropriately weighted. You know, for example, saying that CZ gates are more important. Errors on CZ gates are more detrimental, so they're weighted higher. Distance is an extensive property. It is just like, what is the diameter of your chip, right? And so it's tempting to think of these as two independent things. I can make my components better, or I can make my chip better. And that's a convenient way of thinking about things. Reality is that it is difficult to change one of them independently. If you make a bigger chip, it's very difficult to get the same performance as you got in a previous smaller chip. So that's maybe just like on the applied side. Like if you make a bigger chip, you now have more potential for crosstalk, for example. And so you have to actually account for these things. But from a conceptual perspective, you can think of lambda as quality of components and distance as just being size of the chip.
So increasing distance would worsen your lambda.
It can. The goal is to not have that happen.
Yeah.
Yeah.
But in that paper there, you were able to maintain a lambda of 2.14 till distance 7.
That's right.
Okay.
Yeah.
Maybe higher. That's when it really falls apart.
Oh, I think maybe I'm understanding your question. So what I was saying, which is a little bit different, so I'll try to clarify, is that going from one device generation to another, you know, we want to scale up, we want to make bigger chips. That next bigger chip, it is not automatic that it has the same component performance as the previous chip. There's work involved to make that happen. However, within the same chip, the components are fairly homogeneous. I'm waving my hands because there's a little bit of outliers and they cause some problems, but fairly homogeneous. And in that case, lambda, well, under the right circumstances, and this touches on a topic for the second half, the later talk, under the right circumstances, you will continue to get lambda suppression as you scale. And then there are important ways in which that story can fall apart, which actually motivates some of what I'm going to talk about later.
Okay.
Yeah.
I look forward to it.
Yeah, I'm referring in this case to leakage. Leakage can make the story fall apart.
How often are corrections being performed in your error correction cycle?
So the duration of a cycle is 1 microsecond, approximately. And the unitary part of that cycle, if we go back to this diagram, when I mean unitary, I mean these gates that are not measurement and reset. Those take, I forget the exact number, somewhere between 200 and 300 nanoseconds. And then this is something like 700 nanoseconds for measurement and reset. And so there is nothing else. There's nothing in between. So we are doing unitary gates, we're doing measure and reset, then we go back to doing unitary, yeah. Okay, so where's the correction in quantum error correction? the short answer is this is all done in classical processing. There's like a classical accounting scheme that keeps track of errors that have happened. So a common misconception about quantum error correction is that you correct errors immediately. And in reality, you almost never do that. And the reason is you don't really have to. These errors, if I, for example, think that an error happened to this qubit at the beginning of the circuit, instead of doing anything about it, which by the way is a hard thing to do, that type of fast feedback is technically challenging. Even if I had the ability, I don't have to. And the reason I don't have to is I can keep track of the errors that have happened, and I can use that to update my interpretation of future measurements. And that story continues to hold true for all of the experiments we're doing here and will be doing for a little while. Eventually, you want to do what are known as non-Clifford operations, and that's the point at which you have to start reacting and changing the gates that you do to reacting to the errors that have happened. But for now, it's all classical processing that's recording errors that have happened, but not actually changing anything about the quantum processor based on that history of measurements. Yes?
Can you go to the next slide?
Yes, of course. This one or further?
The one which has the timing. Yeah, this one. So, do I wait for a particular error threshold to be reached for this qubit to use with another qubit?
Do you wait for a particular threshold?
So, to use this logical qubit,
Yes.
do I wait like, some T amount of error correction cycles for this to be used with another logical qubit, or I just let the error propagate?
I think maybe what you're getting at is how does this fit into a fault-tolerant quantum computer? What would it look like when I want to do error-protected computation? So all we're doing here, and it's all that we can do with the current generation of devices, is we make a surface code and then we turn on its error correction to preserve a logical qubit as a memory. So we're just showing that the qubit we started with stays in its state, and the fraction of the time that it's not in the right state is what's plotted here, logical error probability. Now, when this fits into a quantum computer in the future, you're going to need to have multiple surface codes, and these surface codes are going to have to interact with each other. And so the sequence of interactions is the fault-tolerant algorithm. So of course it depends on what that algorithm is, but the gates in that algorithm, the logical gates, will be operations that change the structure of surface codes in local ways. So for us, this is not all quantum error correction everywhere, but for us, local changes to these surface codes. And the way to think about it is that logical gates will take approximately d cycles, where d is the code distance parameter. Simple explanation for that is inside of gates, there are certain logical errors that can happen that depend on the duration of the gate. So the gate itself has to be stretched out in time in the same way that with these codes, we're stretching them out in space. Yeah. Sorry, did you have a follow-up?
Yeah, I have one more question. When you say error correction cycle, I'm guessing that you measured the syndrome and then you decoded and then you applied a conjugate of error. What algorithm are we using here for decoding?
All good questions. I will definitely address these in more detail later. But the way that we're doing it is there are two forms of decoding. There's offline, meaning we send the measurements off to some server and then we look at them. And then there's real-time decoding, which means that we have a special decoder, a special workstation computer that is attached to the experiment using a very high-speed link that allows us to be running the decoding while the experiment is running. We do both. They can work differently. Generally speaking, it's hard to make your best decoding algorithms real-time. So the most accurate decoding today is done offline because you have an unlimited time budget. The real-time decoding, which is ultimately what you need, it has its own decoding algorithms that are a little bit less accurate because they're designed for speed.
Sorry, I have a follow-up question. So for the offline decoding, since real time you need you have a time constraint and everything, do you have some time constraints on the offline decoding as well?
It's human timescales. Like, how long are you willing to wait? There are, in a total experiment, I don't know the numbers, something like millions of shots, because it's like 50,000 per point times how many points. And then you, depending on the complexity of your decoding algorithm, it kind of comes down to like how much time and or how much are you willing to spend on like cloud compute resources. Some decoders are quite fast and can run on a laptop. The most accurate decoders can actually be quite slow because they're based on algorithms that are essentially like a brute force search over an exponential space.
So the offline decoder can take as long as my algorithm is running?
Well, the offline decoding is not representative of a real quantum computer. Offline decoding is you're just saying, what's the best I can do in theory, with no time budget. But that is informative because it might tell you what to aspire to with real-time decoding. Like at what point is real-time decoding almost as good as it's going to be, and you can stop improving it. It's useful for that information. What are the limits of decoding? But it's not actually practical. You can't run offline decoding in a quantum computer because you need that information in real time.
Sorry, I just have a really quick question. I was just wondering whether are you able to, or can you like use d equals 5 or d equals on the d equals 7 surface code and sort of stack surface codes to do like transfers and CNOTs or stuff like that?
I mean, we can't. Not right now. In principle, could you? Yeah, you could imagine some sort of 3D integration. If you recall from the beginning of the talk, the transmon qubits couple capacitively. So in principle, you could have two chips that are really close to each other on top of each other. In principle, you could have some large 3D structure. It becomes an engineering problem, is the short answer. Like, can you build that and get all the wires in that you need?
What is the need for real-time decoding, since we are like just storing syndrome values and like later figuring it out how the error might have propagated?
Yeah, good question. So the reason why you need real-time decoding is that in a fault-tolerant quantum computation, and that means you're doing logical gates. So here, we're not doing logical gates. But when you're doing logical gates, some of those gates, the so-called non-Clifford gates, require that you have feedback from error correction into the system before the gate is even finished. You can't move on until you have that feedback. And so the latency of that feedback, which I'll touch on with real-time decoding, we measured latency of real-time decoding. That latency will set the speed of your quantum computer. And so if it's unbounded, as we're currently doing with offline decoding, then the quantum computer kind of never finishes.
Okay. Right? But that is not required for the threshold plots, right?
For the what?
Real-time decoding is not required for generating threshold plots, right?
Correct, yeah. You can generate threshold plots just from simulations if you have an error model that you like. You can also generate them from experiments, if you have a way of tuning the errors to see when you're at threshold. Yeah. And all of that can be done with offline decoding. Yes?
So for that black curve, the 2023 work, so if I remember correctly, it achieves suppression of logical error rate, but not exponentially. So what's the key factors that contribute to this exponential suppression of logical error rate completely?
Yeah, I did forget to mention this guy over here. Oh, it's so long ago. This was a previous generation device where we showed that lambda was 1, or slightly higher than 1. And you can see that visually because the gray and the black traces are the two code distances, 3 and 5. I'm not even sure which is which. Maybe the black ones are 5. But they were on top of each other, which is what you expect when lambda is equal to 1, because you go up in code distance and you don't improve in logical error rate. And I think you then ask, like, what changed? And a lot is the answer. I don't even have time to tell you everything, but the device got better. we made lambda better by improving all the components, all of the gate error rates.
Only because of hardware improvement or other components like
Decoding got a little bit better too. That was a modest in comparison to the hardware improvements, but yeah, there were some improvements to the decoding as well.
Have you tested your expansion instruction, for example, the surface expansion, logical expansion, expand a distance 5 surface code to a distance 7 surface code on your device? Because I think the expansion instruction is the main instruction in the lattice surgery, which is used for the logical operation.
So let me ask you a question just to clarify. When you say expansion, do you mean if I have a distance 5 surface code, but I have extra room on the device, I expand it from 5 to 7? We haven't shown that here. That is something you can do. I mean, it's a dynamic process, so I can't just off the cuff say what the error rate would be. Probably limited by the amount of time it's at the lower distance will be contributing most of the error. As you can kind of see here, per cycle, you have a higher error rate when you're at distance 5 than distance 7. But it being a dynamic process, it would be some blend of these two.
Would you happen to know like what part of the hardware might have contributed most to like the lambda increase? Like chip fabrication or like wiring, control electronics?
I mean, if you're going to pick a single thing, I think it's improvements to T1. There were improvements in a lot of areas, and at some point, you improve something until it's no longer the limiter. So that you have to improve a lot of things at the same time. But I do think T1 probably carried the most weight for this, if you had to pick a single thing. So coherence.
You're saying that calibrating the qubits is a very involved process. How scalable is this calibration as I scale the chip up, like to achieve larger D in the future?
If you go to March meeting, you should ask that question in one of the sessions. A very hot topic in the field. It of course depends on the way you've designed your device. So more control knobs means more things to calibrate and more ways in which those control knobs interact with each other. So you can get nonlinear interactions, like increase control knobs by a factor of 2, but things you have to calibrate goes up by more than a factor of 2 because of interactions. Yeah, it's a really important challenge for scaling up. I don't have a simple answer other than to say quite a few smart people are thinking about it. Maybe, could I do a quick time check? How are we doing?
15 minutes.
Okay, yeah, I think that'll be fine. So the final part of the final section in the first part, what I'm calling under the hood. So we did that experiment. We got this nice result. It confirmed what we wanted to see. But in some ways, like that's like the very last part. You've done all this work, and at the very end, you see this great plot. So what happened behind the scenes that got us there? And that's kind of what I wanted to talk about. Because we made some improvements, but we also made some discoveries. That's kind of cool. So from that 2023 result, remember that was when Lambda was 1, we improved our device performance. It says 2024, but actually, yeah. If you look at, say, CZ error rates, they went down by like a factor of 2. It's maybe not so easy to like eyeball that, but you'll see that everything shifted down. Everything got better. But the biggest one was T1, which I guess now I know the numbers. Went from 20 microseconds to about 70 microseconds. That was a big jump. And T1 plays a role in, it's not always the dominant contribution, but it plays a role in every one of these operations because it's always there. It's just background environmental decoherence.
I assume that's a mean. Did the distribution change? Did it tighten up?
That is a good question. I don't know.
Because you always worry about like if you really got one.
So T1 is, and distributions of T1 is another fascinating question to ask at March meeting in the right session. A lot of study of that as well. T1 is different for every qubit, and not even for every qubit, it changes with time. So you warm up a device, you cool it back down, you measure T1, you'll probably get different answers. Not always by a lot, but it will move around. And in some cases, it can move around like on the scale of an hour or so. That is often attributed to these so-called TLSs, two-level systems, which are themselves a fascinating topic that has been explored by the field for decades. They are some kind of unintended quantum system, but usually a very noisy one that interacts with the qubit. Some kind of junk on the device, dangling bonds or who knows what. So T1 can change dynamically in time. So even what you call a distribution is, you have to be even careful with your terminology because from something measured over a minute versus something measured over an hour can give you different answers. Okay, so in a hand-wavy sense, though, these errors improve by a little bit more than a factor of 2, and then we get this error suppression from the distance 7 code, which was fourth order. It was something I mentioned earlier. And as I said, also this like light blue line here, which we call detection fraction. That's the fraction of times a parity check flips value, meaning an error happens somewhere nearby. It also improved by a little bit more than a factor of 2. So there's kind of a correspondence there. Error rates improving by about 2x, detection fractions improving about 2x, lambda improving by about 2x. So I promised that there was a spoiler for this lambda story, and there's actually several, but only one I'll talk about today, which is leakage. So in our circuits, I mentioned these are anharmonic oscillators. That means that they're not restricted to the 0 and 1 states. They can occasionally escape into these 2 states or 3 states, higher excited states. We call those leak states, and they are really troublesome. In particular, they have reasonably long coherence times. It's proportional to T1. They have their own decay rates that are a little bit faster than T1 or 1 over T1, but nevertheless, they stick around for several cycles, QEC cycles, and they really cause problems. The reason is our gates are not designed with leak states in mind, and so when these leak states go into our 2-qubit gates, they more or less cause random errors on the qubits they interact with. And they can do even worse things than that. Leakage can spread around. It can like hop from one site to another. I'll talk about that in the second session. But the point is, we just cannot tolerate leakage sticking around forever. We have to do something about it. And so we insert operations into the circuit that remove leakage. In the interest of time, I won't now talk too much about the details, but the point is that if we have a measure qubit, so that we've done our syndrome circuit, we measure it and we reset it. At this point, this qubit is now it's a resource state. It's in a known state, a 0 state, because we just reset it. It's not entangled to anything. It turns out that we can use it to extract leakage from the system. We do an interaction that will cause a photon to hop over to this guy, and then we reset it again. So this is kind of like an entropy extraction process. We're pulling unwanted excitations out of the system. This is an important part of the story, and in fact, we were exploring this in the past, and when we were closer to threshold, it didn't really seem that adding it made a difference. For this recent experiment, it did. So this is, in this case, only distance 3 and 5, and at distance 3, leakage removal, here at this DQLR, it means data qubit leakage removal, doesn't buy you a whole lot. Ways of interpreting that are, well, distance 3 is already kind of unreliable. Maybe leakage isn't a big part of that story. Also, these are small codes. If leakage can move around, it doesn't have very many places to go. But at distance 5, everything changes. This code is more reliable. It's bigger, so leakage has more opportunities to wander and cause problems. And so without leakage removal, you get this error accumulation rate, and with leakage removal, it improved. And this wasn't pretty significant, actually. This increased lambda by about 35%. So this was an important part of the story. We kind of already suspected it, so it wasn't like a shock to us, but it is kind of cool to see that we're now actually confirming that we needed that. Another thing we did to make this experiment better than the past is we had better decoding algorithms, and we also had real-time decoding. Kind of set it in the reverse order. I'll talk about real-time decoding more in the second session, and then here is a suite of different decoders. I'll explain them briefly. The first three are actually very closely related to each other. They're all variations of an algorithm known as minimum weight matching. This one is like the one you can find kind of used mostly in the literature, and it has been used for surface codes going back to the original works from 2004 or so. The real-time one has some improvements, but it also runs really fast. So we did some engineering to make it really fast. We have an even upgraded version that's even more accurate of matching that doesn't quite run in real time today. And then we have wonderful people, wonderful AI researchers at Google. And so we have a neural network decoder that is today the most accurate for surface codes. And so this contributed about a 15% increase in lambda as well. Yeah.
For that last decoder, how often do you have to update it?
Have to update it?
I don't know, like as your data and your error models change, do you have to retrain things?
It's a really good question. It depends on how much you want to go to the bleeding edge. So this decoder will work really well with a simple noise model, like a poly noise model that is essentially independent of the device itself. You pick reasonable parameters. And then if you really want to tune it for best performance, you can train it on experimental data. In terms of practicality, could you apply this in a real quantum computer? We have found that even though we know that parameters in the chips drift over time, that this decoder is able to work close to optimal, close to its best achievable performance, even using past experiment runs. So the correlations and the errors that it discovers are persistent enough that, yeah, you can in practice train it one day, use it the next day.
Just to understand the plot, minimum weight perfect matching, for example, is not finding more errors. It's just its estimate of those error rates is too high systematically. Is that correct?
So the way to say it is that in error correction or in fault-tolerant quantum computing, the error rate is a function of the errors that happen in the device and the code you're running, and the decoder's ability to identify those errors. So the different variations of decoding are all taking exactly the same data set as input. These are the same measurements, so we've controlled everything except that last step. And these different algorithms are increasingly clever about their ability to understand and identify correlations in the errors.
So can you say something about how big is a neural network? Is it a real-time algorithm?
It is not currently a real-time algorithm. This paper actually has appeared in Nature, so I should have updated this. But that paper gives some additional detail about its performance characteristics. The short answer is that it has a throughput, meaning like you send information to it and it processes it, that is approaching real time. So there's that principle there. But there's an engineering challenge that hasn't yet been solved of how do you actually get this close to a quantum processor in a way that you can send data in and out really fast, like with low latency. That's future work. Because right now it's running essentially on a, in the cloud on a server.
Can you tell a bit about the noise model that was considered in the work?
Do I have a slide on that? We consider noise models of varying degrees of complexity and realism depending on the context we're interested in. So we have, I would say, a fairly complex physics-motivated model, when we want to be really accurate, that model is derived from all sorts of characterization experiments. However, that high level of detail is not always helpful. For example, decoders do not necessarily work well when you just throw something complicated at them. And that's because when they're heuristic, they actually can be deceived by complex noise models. They don't always understand correlations, and they can do weird things because they're heuristic. So for these decoding models, we give them a simplified poly model because just by practice, we see that that works best for that application, decoding. But when we want to try to predict system performance, like I showed a few slides back, simulations of the experiment, in that case, we want to use very accurate models. And those models include crosstalk, they include leakage, a variety of very fine-grained physics details for our devices.
Is it there in the paper?
Is it what?
The details are there in the paper?
I believe they are in the supplement, and also the supplement to the previous paper, the 2023 paper discussed this as well.
I was wondering whether the leakage that you observe, is that tied to particular 2-qubit gate operations or?
Yeah, that's a good question, and I'll go a little bit deeper into leakage in the second session. So you may remember I was talking about two states when I was talking about CZ gates. So CZ gates are a source of leakage. When the gate does the wrong thing, it has a high probability of causing leakage. So when we say CZ gate error, a significant fraction of those errors are leakage. So if the CZ gate has I think it was 3e minus 3 error per gate, then something of order 1e minus 3, a significant fraction, is leakage events. But there are other sources of leakage. Readout can cause leakage just because you're sending a lot of energy into the system. It can cause excitations. There's a few other physical mechanisms that can generate it.
The leakage is in terms of current, electrical current, or what is it?
Oh, in this case, leakage refers to the qubit entering an excited state. So we call them leak states because they are outside of the 0-1 subspace.
Okay. But why is correlated?
Why is leakage correlated?
Yeah.
Oh, I think maybe I understand your question.
Correlated error, yeah.
It causes correlated errors because a way of thinking about it is every time it interacts with one of these 2-qubit gates, instead of doing the correct 2-qubit gate, it will apply like some arbitrary phase rotation here. And then the leakage just keeps going, and then it'll do another phase rotation here and here and here. It does it in a bunch of different places. And those coherent errors will get projected down into some pattern of poly errors by the stabilizer measurement circuit. So it produces these like burst events of errors. And I'm calling them correlated, although what correlated means kind of can depend on context. Oh yes, question.
May I know what algorithm you are using for the second column real time? Because I thought MWPM is near optimal for surface code, but all of them are better than it. And
that's a good question. So the simplest implementation of the minimum weight perfect matching algorithm is to consider the X parity checks and the Z parity checks separately. And so if you have a single type of noise, like you only have bit flip noise, then the minimum weight matching is close to optimal in that case, under certain models. But the fact is we have errors that will cause parity flips of X and Z at the same time. Simplest example is a Y error. It's like being an X and a Z simultaneously. And in that case, this algorithm is leaving a lot on the table. It's not acknowledging that the X parity checks and the Z parity checks can be flipping together because it solves them separately. So we have ways of bringing correlations into this system, which all of these algorithms do. These do it explicitly, like I can tell you exactly how we include the correlations. It's an algorithm. This one does it in AI magic, which, I mean, it learns a complex correlation model. That's what it does, but it's buried in a neural network.
Is there a name for your real-time algorithm?
It is very closely related to correlated minimum weight matching, which has been published. It involves a few heuristic tricks that make it slightly different, but it's very closely related to that algorithm.
And do you see a potential for the neural network method to be real-time in the future?
Yeah, it definitely has the potential. As I was saying, like some timing of it shows that it can process a distance 5 surface code data in about 1 microsecond per round. I don't remember the exact numbers. They're in the supplement of a paper that I could show you. But it's like, it has that potential because if you time it, in offline decoding, it seems to be keeping up with the data. And, I think with a variety of engineering efforts, it could be made real time, yes. But that's work to do.
Just to clarify, so you use the ground truth states for the 0 1 basis and decided states or leakage states, right?
Yes.
So could you potentially engineer your oscillator such that the leakage states are much higher in energy, maybe make it 10 or something, and so it's less likely to?
So, yes, you can. So this is now venturing outside of my expertise. There are very many different types of superconducting qubits, and I've only talked about one of them here. So I can certainly point you to review papers on the sort of zoology, if you will, of all the different superconducting qubits. There's different ways of arranging Josephson junctions and capacitors to give you lots of different properties. And so you might ask, okay, why are we using one with leakage nearby? It turns out that transmon qubits have some other nice properties. They're very controllable, meaning like it's easy to put them in an array, like a 2D array, and have them talk to 4 neighbors. And there are other superconducting qubits that may be resilient to leakage, but it's hard to get them to couple to each other. So different teams are exploring different approaches, but they're all facing trade-offs, is the way to put it. And we made a particular choice that's oriented towards qubits that can easily be put in a 2D array.
Is there any chance the synthetic matching decoder is open source, or is it like proprietary?
Well, there is a paper, so the algorithm is described in a paper, but we have not open sourced it, or we haven't done so yet. I guess Richard's telling me that we're out of time.
I was going to say, take a couple of minutes if you want to finish up a few things before we take a break.
Okay. I'm mostly going to skip this one. It only shows you that the device is pretty stable. That is not something to take for granted. So this means that we ran the same experiment many times over 15 hours and got pretty stable results. But other than that, it's kind of nice. Some details here about how calibration was done. But this actually, I think, is a really interesting part of the story. So if I'm going to finish with one thing, I'll say this. In the 2023 paper, which was shown here, we did surface codes, as I described here, but we also did repetition codes. Repetition codes are 1D codes. They form a line. So it's zigzagging like this. So even though it lives on a 2D grid, it is essentially a line, but that line is just snaking around. And that means that we're only measuring parity checks in a single basis. So for example, we may only be measuring them in the Z basis. That detects bit flip errors. And this is a really large code. In fact, it's distance 25, but it's a classical code. It's not really something we would use for a logical qubit. However, it's still quite interesting as a sensor. And the reason for that is repetition codes also have a higher threshold, and so they have a higher lambda value. And so by going to very high distance and having higher lambda, we can probe very low logical error rates. Remember, it's a classical code. We can't use it for quantum computing, but still, we can make it hold information very reliably. in a quantum processor that's using all of the toolkit of a surface code. All of the operations are there. So we can use this to measure interesting effects. One of those effects is we ran this experiment, and then we saw that there was a noise floor. And it just kind of just happened to, we got lucky, right? In a sense, lucky in some sense, that we were just able to see it. This noise floor is right here, which is just within the range that the sensor is able to pick up. Right? This is 10 to the minus 6. And we did a lot of study. We attributed this to high energy events, some high energy particles striking the chip, generating cosmic rays, where I think that it may be, well, I'm not the expert, but I hear that it could be more than one thing. So that's kind of interesting. And remember, our surface codes are up here. Their logical error rates are up here. So we would be years away from seeing this effect if we didn't do this experiment. So the repetition codes are a sensor that are telling us about problems in the future. And then here we have some data points where the noise floor goes away, and that's because we actually post-processed. We went and we looked at the experiments and we said all the bad ones happened consecutively. They were all right next to each other. And we did additional corroborating experiments. Here's all the bad ones next to each other, by the way. That lighting up is errors happening on the chip. And I don't know if this video repeats. I'll do it again. So it starts off really well, and then it gets very bright, and that's because the rate of errors happens in this big burst pattern, and it's lasting, as you can see here, over milliseconds. So not only is there a jump in error, but it hangs around for a while. That's because quasi-particles, excitations in the device itself are being excited, and they have a relatively long decay time. I am not actually sure. I wish it was labeled. It is something related to errors per unit time, but I am not actually certain. So we made a new generation of devices that are so-called gap engineered. There's a citation there if you want to go and read the details, but they are now very resilient to these high energy events. So that was another improvement that we made to our devices. And to really show the effect, we made a test device where we made a grid of qubits. This is the grid of qubits, and we interleaved the ones that were old style and new style. And you can see in time that when we ran the experiment long enough, found one of these events, that they're happening, and the new improved qubits are now resilient to this error source. And we thought this was great. We're like, all right. We had this like existential crisis, this is like the asteroid coming for the dinosaurs. And then we solved it. Or did we? This is that same data from before in gray, the repetition code 2023. And then we ran it again on the new device. Remember, the new device is about twice as good. So, and it's bigger, can go even larger. And so we get a higher lambda. So this is now an even steeper line. And we can go to higher distance. Then what happened? So we got a lot lower error rates. This is now 10 to the minus 10. This is 10,000x or 4 orders of magnitude lower than the previous noise floor. But it's there. We're not yet sure what it is. We're working on it. These are quite hard to diagnose. This is about 1 event per hour. So it takes a lot of time to even see these errors. But it's kind of cool. This is sort of in the regime where we need logical qubits to be, but we don't want a noise floor. We want it to go away. So we're working on it. But it's kind of, I think, interesting that we're able to use error correction as a sensor. We're seeing something that doesn't have a simple explanation. Yeah, question.
Do you have a guess for what it might be?
I don't, because this is now getting into physics that is outside my area of expertise. But I know that we have some people working on this who have some ideas.
All right, I would say, why don't we yeah, he's going to be here for a long time. Why don't we go to the break and reconvene at, say, like 5-ish after 4. And the 8 of you who are about to pounce under the carpet. Who likes to